Ladies and gentlemen, welcome back to chapter 4 of our course on linear algebra in 2D. We'll be talking about bases and inverse matrices today. So essentially in this video we will take a first step to better understand different coordinate systems and how they relate to linear maps. First we will be talking about bases as different coordinate systems, then about invertible matrices and linear maps and their properties, and finally we will learn how to compute the inverse of a matrix if it exists. Let's start with bases. Now recall from our previous chapters that every vector x in the plane with coordinates x1, x2 is a linear combination of the two canonical basis vectors e1, e2. So this is e1, the first canonical basis vector, this is e2, and if x has the entries x1, x2, then this is the same as writing x1 times the first canonical basis vector plus x2 times the second canonical basis vector. So it's x1 times e1 plus x2 times e2. And these two numbers, x1, x2, are called the coordinates of the vector x, expressed in the canonical basis, so with respect to these two vectors here. Now the canonical basis is not the only way to define coordinates in the plane. So up to now it has been our way of defining coordinates, but it is not the only way we can do this. So what does it take to define coordinates? That means we want to have a way of uniquely identifying every point in the plane by a suitable pair of numbers. And it turns out that any pair of vectors that is not lying on the same line can define a coordinate system. Let's make this more precise. Two vectors, x and y, are called linearly independent if x is not a multiple of y, and then vice versa, of course. So precisely this means x is different from lambda times y for any scalar lambda. And in particular, this requires that both of these vectors, x and y, are different from the zero vector, because if one of them was 0, for example, if x equal to 0, then we could always multiply y by the scalar 0, by the number 0, and this inequality would not hold. So therefore both have to be different from 0 if they are to be linearly independent. Now here we have this geometrically, so we have a vector y here and a vector x here, and they do not lie on the same line, so they are linearly independent. Whereas, for example, here we have a multiple lambda x of x, which of course does lie on the same line, so x and lambda x are not linearly independent, and the same for different multiples like mu x, they're also not linearly independent, those two. Now our first proposition gives us a different characterization of linearly independent vectors. So we say that two distinct vectors x and y are linearly independent if and only if, for any scalars lambda mu, the equality lambda x plus mu y equal to 0 implies that lambda and mu are both zeros. Okay, so whenever we can write x and y in such a linear combination that gives 0, then if and only if they're linearly independent, this forces lambda and mu to be equal to 0. Now the proof goes as follows. First we show the direction where we assume that x and y are linearly independent, and we want to show that if we can find any such lambda and mu such that lambda x plus mu y is 0, then lambda and mu must be 0. So they're linearly independent, and we let lambda and mu be any scalars. And we assume, for contradiction, that one of them is non-zero. Say lambda is non-zero. And we also assume that lambda x plus mu y is equal to 0. Then, because we assumed lambda is not 0, we can divide by lambda, and we have x equal to mu divided by lambda times y. But this means x is a scalar multiple of y, and this contradicts our assumption of the linear independence of x and y. So by this contradiction, we cannot have this, that one of them is non-zero, so both of them must be 0, and we've shown this bit. Now we prove the opposite direction. We assume the second statement holds, so that lambda x plus mu y equal to 0 requires lambda and mu to be both 0. And we want to prove that in this case x and y must be linearly independent. So for contradiction, assume x and y are linearly dependent, so that there is a scalar alpha such that x is alpha times y. But then we can just subtract x on both sides here, and we get minus x or minus 1 times x plus alpha y equal to 0. But this contradicts our assumed requirement here that the scalars in such a linear combination must both be 0, because lambda equal to minus 1 clearly is not equal to 0. And we don't know anything about this alpha. Now, by this contradiction, it follows that x and y must be linearly independent, so that this assumption here cannot be true. And this proves, together with the first part, our theorem, our proposition to be precise. Now, the equation 1 in the previous proposition, this one, implying lambda equal mu equals 0, can be generalized to an arbitrary set S of vectors. So the set S is called linearly independent if for any distinct elements x1 to xk from this set and scalars lambda 1 to lambda k. And when we have such a linear combination, lambda 1 x1 plus lambda k xk equal to 0, then this implies that all the lambdas from lambda 1 to lambda k must be equal to 0. And another way to say this is that no vector in S can be written as a linear combination of the other vectors in S. So, for example, if x1 could be written as a linear combination of x2 to xk, then we would have some expression x1 equal to linear combination of the others. Then we could subtract x1 from this, and we would get an expression of this form equal to 0. But if this implies that all the scalars here must be 0, then we could not have had x1 expressed as a linear combination of the others in the first place. And if this property does not hold, so if we can find a linear combination of x1 to xk of certain elements from the set S where not all the lambdas are 0, then we say S is linearly dependent. And this is actually the usual definition of linear independence used for vector spaces of arbitrary dimension. But in our two-dimensional case, I think it's more intuitive to use the definition that two vectors are not proportional to one another. Whereas if you have higher dimensional vector spaces, such a geometric expression or a geometric definition would be more complicated to make, so it's easier to go with this property for the definition. Now let's look at some examples. So with this definition of linear independence, we can say that the empty set is linearly independent. So this may appear a little bit strange, but if S is the empty set, then, well, there are no vectors in S, so this whole condition here is void and so trivially satisfied. And therefore the empty set is formally linearly independent. If we have a set S which contains a single vector that is not the zero vector, then this set is linearly independent. So a single vector is linearly independent. However, if it is the zero vector, then it is linearly dependent, because if you think about it, if let's say there's only one vector in S, and that's the zero vector, then we could write zero vector times any scalar and we still would get the zero vector. So the zero vector alone, or any set containing the zero vector, actually does not satisfy this condition for linear independence. And now any set S of vectors in the plane that contains more than two vectors turns out to be linearly dependent. So we can think about it in the following way. So either all the vectors in S are multiples of each other, well then they are clearly linearly dependent, because any two of them are already linearly dependent. Or S contains, if this is not the case, then S contains at least two linearly independent vectors, b1, b2. So these two are not multiples of each other. And then we have the following theorem 3 that tells us that any third vector in S is a linear combination of b1 and b2. And by what we observed here, this means that the set S is linearly dependent. And we call a pair, b1, b2, of linearly independent vectors a basis. So note that this pair is ordered, so the order of the two vectors here actually matters. And we have theorem 3 that I already referred to before, which states the following. If we have two vectors, b1 and b2, then the following statements are equivalent. The first statement is every vector x can be written as a unique linear combination of b1, b2 for the corresponding scalars lambda mu, which means x is equal to lambda b1 plus mu b2. And as it says here, it's unique, so there's only one pair lambda mu for which this linear combination exists. And the second statement, which we claim is equivalent to the first one, is that b1 and b2 form a basis, so they are linearly independent. And if this situation is the case, so if b1 and b2 are linearly independent and we can write x as such a unique linear combination, then we call these two scalars lambda and mu the coordinates of x in the basis b1, b2. And you see this is perfectly analogous to what we had before, when instead of b1, b2 arbitrary vectors, we had the two canonical basis vectors e1, e2, and then lambda and mu were just the coefficients of the vector x. And these were the coordinates in the canonical basis. And now if we have a possibly different basis, b1, b2, then we just say these two coefficients from the linear combination that makes up x are called the coordinates of x relative to this basis b1, b2. The proof of the theorem is as follows. So first we show that 1 implies 2. So we assume the first statement is true, and we will show that b1 and b2 are linearly independent. So if the first statement is true, we can write x as a unique linear combination lambda b1 plus mu b2. In particular, the zero vector can be written as such, so 0 equal lambda b1 plus mu b2. But also we get the zero vector if we just multiply b1 and b2 both by 0. So we have one particular linear combination that makes this true, but we assume that such a linear combination must be unique. So whatever linear combination we have here, it must be this one, lambda equal to 0 and mu equal to 0. But what we've shown in proposition 1, that the fact that it follows that lambda and mu must both be 0 means that b1 and b2 are linearly independent. So we've proven that statement 2 follows from statement 1, and now we do the converse. And this is a little bit more work. So we assume, statement 2, we assume that b1 and b2 are linearly independent, which in particular means that both of them are non-zero. And we want to show now, statement 1, that every vector x can be written as a unique linear combination of those two. Now, we need to recall what we learned in chapter 3 about systems of linear equations. So if we write it out in coordinates, our vector x, x1, x2 is a linear combination of b1 with entries b11, b21, and the vector b2 with entries b12, b22. Then this is to solve a system of two linear equations in the variables lambda and mu. So these are the unknowns that we're looking for, the coefficients of our linear combination. And yeah, I refer you back to chapter 3, section 1, where we discussed this as one of the motivating examples to study linear equations. And this led us to a system of linear equations, which in the extended matrix form we can write like this. So this is the vector b1, this is the vector b2, and here we have our right-hand side, the vector x. And we're looking for the coefficients lambda mu as the unknowns of this equation. And I name this star. And we may assume that b11, so this vector here, is different from 0. Otherwise, we swap the order of the two vectors just to make sure that at least one of the two coefficients is different from 0. And one of them here has to be different from 0, because if b11 and b12 here are both 0, then it's clear that b1 and b2 are multiples of each other, which would contradict them being linearly independent. So that can't be. So at least one of those two must be different from 0, and we will just, for simplicity, assume it's b11. Now, because this is different from 0, there exist scalars alpha, beta, and gamma, such that b12 is alpha b11, b21 here is beta b11, and b22 is gamma b11. And the linear independence of b1 and b2 requires that gamma is different from alpha times beta, because otherwise b2 would just be alpha times b1. So you can check this if you plug in all of these expressions here. If gamma was equal to alpha times beta, then this would be true. Now, what we do here is we divide both sides by b11, both sides of this system of linear equations, which we may do because we assumed this different from 0. And then we obtain another linear system with the same set of solutions. So recall dividing those two equations by a scalar and replacing them is one of the elementary operations on linear equations, so that doesn't change the set of solutions. And yeah, the right-hand sides, x prime 1, x prime 2, are just the corresponding x divided by b11. And here, the left-hand side is the matrix 1 alpha, beta, gamma. So that's what I get if I divide all of these by b11. And from the choice of numbers alpha, beta, gamma, I end up with this system, which I call double star. Now, by direct computation, we can verify that the solution of this system is given by lambda equal to gamma times x1 prime minus alpha x2 prime divided by gamma minus alpha beta. Recall this is non-zero because we assume b1, b2 to be linearly independent, so we can divide by this. And mu equal to x2 prime minus beta x1 prime divided by gamma minus alpha beta. Now this is maybe a bit much to swallow, but if you take these two numbers, lambda and mu, and plug them into this system of equations, so if you take the matrix notation, write it back out as a system of two equations in the variables lambda and mu, and then you plug this in for lambda and mu, you will indeed find that this is a solution of the system double star. And now we make some non-trivial use of the solution theory for two linear equations in two variables from chapter 3, more precisely theorem 12 in chapter 3. And that stated that every solution x of every solution lambda mu for this equation here, so x equal to lambda b1 plus mu b2, is the sum of a particular solution, lambda tilde mu tilde equal to blah blah blah, what I just presented to you on the previous slide as a solution, plus some solution of the homogeneous system, lambda b1 plus mu b2 equal to 0. Okay? But by the linear independence of b1, b2, and by proposition 1, the only solution to this homogeneous system is lambda equal to mu equal to 0. And that means if all solutions are given by this particular solution plus a solution of this, but this only has this trivial solution, then we have actually a unique solution here. So we have a unique linear combination x lambda tilde b1 plus mu tilde b2, where lambda tilde mu tilde are given by these two numbers. And that concludes the proof that we assumed that that b1 and b2 are linearly independent, and we concluded that any vector x can be written as a unique linear combination of these two linearly independent vectors. Now we explore the property of linear independence further in theorem 4. So again, we have two vectors, b1 and b2, which are again write out in coordinates. And B, capital B, is the matrix which has b1 and b2 as columns. So I take the coordinates here and just write them next to each other as columns in this 2 by 2 matrix, which I call capital B. And then the following statements are equivalent. First, the vectors b1 and b2 are linearly independent, or in other words, they form a basis. This is equivalent to, second, for any vector y, taken as the right-hand side of a linear system, the linear system b times x equal to y has a unique solution x. And both of these, in turn, are equivalent to the third statement. The homogeneous system of linear equations, bx equal to 0, has only the trivial solution x equal to 0. And we don't need to prove anything more for this theorem because it follows directly from theorem 3 that we just proved before, since asking for a solution bx equal to y is literally the same as asking to write y as a linear combination of the vectors b1 and b2, where the coefficients for the linear combinations would just be the two entries of the vector x. So essentially this is just rephrasing what we proved before, but in an interesting and more clarifying way. And now it's time for some examples. So consider the pair of vectors b1 and b2 given here. b1 is 1, 0, so just the same as the first canonical basis vector, and b2 is 0, 3. Now, clearly these two vectors are linearly independent because, well, one can't be a multiple of the others because this one has an entry 0 here, where this one has a non-zero entry, and also this one has a 0 entry here, where the other one has a non-zero entry. So there's no way these two vectors could be multiple of one another. So B, this pair here, is a basis. And now we have another pair, B tilde, given by b1 tilde, b2 tilde, and this is the vector 1, 1 and the vector 2, minus 1. And here it's maybe not completely obvious that they're linearly independent. So we can show this by studying the homogeneous system b tilde x equal to 0. So if we can show that this only has the trivial solution, then we find that these two vectors are linearly independent. And note my sloppy yet convenient notation here. I use the b tilde symbol for both the basis and for the matrix which contains the two basis vectors as columns. So that's Basically, I'm just dropping this comma here. And yeah, maybe a little bit sloppy, but it's convenient, and it's, of course, you understand what is meant by it. So I will continue to use this slight abuse of notation. Now, let's check this. We apply some elementary operations, which we learned about in chapter 3, section 3, to reduce the system. So yeah, what I do first is I subtract the first line from the first row from the second row, and I end up with this system. Then I divide by -3, ending up with this system, and then I subtract twice the second row from the first row, and I end up with this matrix 1, 0, 0, 1. And if you recall the solution theory, then we find that there's only one solution to the homogeneous system, which is the trivial solution x equal to 0. And by what we just learned about bases and linear independence, this means b tilde 1 and b tilde 2 are in fact linearly independent, so this is truly a basis. Now, theorem 3 told us that any vector, and in particular this vector v with entries 4, 1, can be written as a linear combination of both the vectors in basis b and the vectors in basis b tilde. And I've actually done this here geometrically. So the vector 4, 1 is here, is v. You take 4 steps in the direction of v, of b1, and 1 step up. And yeah, but b2 is actually 3 times the first canonical basis vector. So this 1 step up is actually just 1/3 of b2 that you go up here. So 4 times b1 plus 1/3 b2 gets you to the point v. And similarly, you can write v as a linear combination of b1 tilde and b2 tilde by going twice in the direction of the vector b1 tilde and adding to this once the vector b2 tilde. So this vector here added at this point gets you exactly to the vector v. Now, of course, this is a picture as a proof, and it's quite easy to do it with this vector with its very friendly numbers. But of course, it doesn't work as easily for arbitrary vectors. So we want to know how we can do this algebraically. And what this means is, given our vector v with entries 4, 1, we want to find scalars lambda and mu such that lambda b1 plus mu b2 equals v. And if we write those two out, so it's lambda times 1, 0 plus mu times 0, 3. And this means we have to solve the inhomogeneous linear system with b1 and b2 as the columns and the vector v as the right-hand side. And we can easily do that because it's a very simple system. We just have to divide the second row by 1/3 and we end up with our solution lambda equal to 4 and mu equal to 1/3. And so we find that the vector v, 4, 1, is equal to 4 times the vector 1, 0 plus 1/3 times the vector 0, 3. And you can easily verify this, of course, by adding these two vectors. Now, as an exercise, pause the video and do the corresponding computation for the basis b tilde. So determine scalars lambda tilde and mu tilde such that our vector v is lambda tilde b1 tilde plus mu tilde b2 tilde, or explicitly written out this linear combination here. So I hope you gave it some thought. Let's look at the solution. What this means is we have to solve the inhomogeneous system using elementary operations we learned about in chapter 3. So here we have b1 tilde as a column and b2 tilde as a column and v as the right-hand side, and our unknowns are lambda tilde mu tilde. And we can apply some elementary operations by first subtracting the first row from the second row. And then we divide by -3 in the second row to get this system. And we subtract twice the second row from the first row to arrive here. And we can read off the solution, lambda tilde equal to 2 and mu tilde equal to 1. So we find that v, the vector for 1, is 2 times 1, 1 plus 1 times 2 minus 1. And again, you can easily verify that this is correct. So we have found how to represent v as linear combinations of both bases b and b tilde. And of course the representations are different because the bases are different. And now a reasonable question is, if we are given two different bases, how can we compute the coordinates in the second basis when given the coordinates in the first basis? So for example, if we know the vector v and we know that it is this combination in b1, b2, and is there a way to get the representation for an arbitrary vector in the basis b tilde? And we will answer this question in the next chapter of this course, and it's actually quite an involved answer where we can learn a lot about coordinate systems. But before we can do that, we need to take another look at linear maps first. Namely, we need to study the property of invertibility of matrices and linear maps. First, I introduced the identity matrix, which we have actually seen quite a few times in our linear equation systems. More precisely, the 2x2 identity matrix, which I name I2. So the capital I with index 2 stating that it's the 2x2 identity matrix is just the matrix with ones on the diagonal and zeros otherwise. And we can compute that for every vector x and every matrix T, we have identity matrix times x is equal to x, and identity matrix times T is the same as T times identity matrix is equal to T. So multiplying by the identity matrix doesn't do anything to the object that it's multiplied with. And in this sense, the identity matrix works a little bit like the number 1. If you multiply any number by 1, then the number stays the same, and this is like the number 1 for matrices. That's also a reason why we choose this notation, because this capital I doesn't just stand for identity, it also can be seen as representing the Roman numeral 1. So that's quite convenient. And geometrically, it is just a trivial transformation that doesn't do anything on the plane. And now we say that a matrix A is invertible if there exists a matrix A to the power of -1 such that A times A minus 1 is equal to the identity matrix, and also A to the power of -1 times A is equal to the identity matrix. So recall that matrix multiplication is not commutative, so we have to explicitly require both of these properties here. So we call this A to the power of -1, or often we just call it A inverse or the inverse of A. And we can think of the inverse of A as the transformation matrix that reverses the effect that A has. So if A is interpreted as some geometric transformation, then A inverse undoes whatever A has done. And again, the notation here is reminiscent, of course, of numbers. If you multiply a number by a number to the power of -1, you get 1. And in the case of matrices, we get the matrix that corresponds to 1 in the matrix set. And observe, which is clear from this property here, that the inverse matrix of the inverse matrix is A itself. So if A has an inverse, then automatically the inverse also has an inverse which is just the original A. And as examples, I recall the 4 types of transformation matrices we encountered in chapter 2 of the geometric transformations that were invertible. First, rotations. So a rotation matrix R alpha, so rotation by angle alpha is invertible, where the inverse matrix is simply given by the rotation by the same angle but in the opposite direction. So R minus alpha is the inverse of R alpha. Because, as we saw in chapter 2 already, if we have 2 rotation matrices, R alpha times R minus alpha, then this is the same as rotating by the sum of the angles, but alpha minus alpha is just 0, so rotating by angle 0 does nothing at all, so this is the identity matrix. In particular, this means the inverse of a rotation is also a rotation. And for reflections, it's even simpler. A reflection matrix is its own inverse. So if S is the reflection matrix for a reflection across some axis going through the origin, then S multiplied with itself gives the identity. So S is equal to S inverse. And yeah, if you think about it geometrically, you reflect some image across a line and then you reflect again. That just means mapping the image back into its original position. Then recall we had shearings, and a shearing matrix N has an inverse. So if N is this shearing matrix, this upper triangular thing as we call it, with ones on the diagonal and a coefficient A here, then its inverse is just the matrix with ones on the diagonal and minus A up here. And we can easily check this by computing the product, and then we get 1 on the diagonal, and here we get minus A plus A, which of course is 0. So we are left with the identity matrix I2. So this is in fact the inverse. And in the same way you can verify that n minus 1 times n is also equal to the identity matrix. And we observe, similar to what we observed with the rotations, that the inverse of a shearing matrix is also a shearing matrix, just with the negative coefficient here. And then we also had scalings. So these were the matrices which had 2 non-zero entries on the diagonal and 0 on the off-diagonal. And if A is a scaling matrix with diagonal entries lambda 1, lambda 2, then the inverse is again a scaling, where we just take the inverse values of lambda 1, lambda 2 as diagonal entries. And then you can directly verify that this is true by simply multiplying the diagonal entries. Now we have an interesting case where the matrix is not invertible. So yes, these cases do exist. Not every matrix is invertible. And recall that we had projection matrices in chapter 2. So we had these 2 matrices for projections on the E1 and the E2 axis. So the axis spanned by the 2 canonical basis vectors. The projection on the E1 axis is given by 1, 0, 0, 0, and the projection on the E2 axis is given by 0, 0, 0, 1. And these, I claim, are not invertible. And let's prove this. So if A is any arbitrary matrix with these entries, and we multiply A by the P1, by the projection on the E1 axis, then we get the matrix A11, A21, and 0 in the second column. What that means is it is impossible to have any matrix A for which A times P1 is equal to the identity matrix, because the identity matrix must have an entry 1 here, but there's no matrix A for which this can happen. So this means P1 cannot have an inverse. And in a similar way, you can prove that P2 also cannot have an inverse. So here we have some geometrically relevant examples of matrices that are not invertible. And let's take a geometric look at this property of non-invertibility. And recall that we think about inverse matrices as something that reverses the geometric effect. And if the projection matrix P1 was invertible, which we know it isn't, but if it was, then the inverse matrix P1 inverse would define a transformation that reverses the effect of P1, which in particular means if we take the projection of any vector x by the matrix P1 and then apply the inverse, we would have to get the original vector x back for any vector x. But for every value P1x, for every projection of a vector x, there are infinitely many distinct vectors being projected to the same vector. Okay, so if this is our x and we take the projection down here onto the first axis, then any other vector lying on this blue line here above this projection value is projected to exactly the same point here. So projection of x is the same as projection of y, is the same as projection of z, and same for any other point on this blue line. So there is no unique vector x that we could get back by applying a possible inverse. And this is in fact the characterizing property of non-invertibility, that you can't really say which value was mapped to this projection here, because there are multiple values that could have been mapped there. This sums up what I just said. If we know P1x, then we don't have a uniquely defined original vector x, because it could have been y, it could have been z, or any other vector here. So there can't be, by geometric reasoning, an inverse matrix that reverses the effect of the projection. And we can also define invertibility for linear maps. So recall that linear maps correspond to matrices. We can express the effect of a linear map by a matrix vector multiplication. And so we can define invertibility for linear maps as well. And we do this as follows. We say a linear map phi is invertible if the matrix A that represents it in the canonical basis is invertible. So if we write phi of x equal to A times x for some matrix A, then we say phi is invertible if this matrix A is invertible. And the inverse map phi inverse phi to the minus 1 is then determined by the inverse matrix A to the power of minus 1. Yeah, so what it means, phi being invertible with inverse phi to the power of minus 1 is just phi composed with phi to the power of minus 1 equal to the identity map, so the map that maps every element of the plane to itself. And this is also the same as phi to the power of minus 1 composed with phi. And moreover, for every vector y, there's a unique vector x such that phi of x is equal to y. Namely, x is given by phi inverse applied to y, which is the same as phi inverse applied to phi of x. And once we have proved the upcoming theorem 12, then this uniqueness property here is a reformulation of theorem 4, part 2, about basis vectors. Now we need another important concept of linear maps. We say the kernel of a linear map, phi, or of a matrix A, is the set of vectors that is mapped to 0 by this linear map or by the matrix. So the kernel of phi is the set of all those vectors x such that phi of x is equal to 0. Or for the matrix A, we say the kernel is the set of all the vectors x such that A times x is the 0 vector. And of course, if A is the matrix representing the linear map phi, then the kernel of A is the same as the kernel of phi. And we have a proposition on the kernel which characterizes it geometrically. The kernel of a linear map phi, or if you want the matrix A, is a linear subspace of the plane. And a linear subspace means that it has these two properties. Firstly, if we have two vectors in the kernel, then the sum of these two vectors is again an element in the kernel. So if x and y are mapped to 0 by phi, then their sum x plus y is also mapped to 0. And the second is if x is an element in the kernel, then any multiple of it, so for any scalar lambda, the multiple lambda x is also in the kernel. And in particular, this means that 0 is an element in the kernel of any linear map phi. And this is a very important property of the kernel, and it's especially important in higher dimensional vector spaces. The proof is very simple, because we just use the linearity of phi. So x and y are elements of the kernel, so they get mapped to 0 by phi. And lambda is any scalar, and we just use the linearity, as I said. Phi of x plus y, so we look at the sum, is by linearity phi of x plus phi of y. And by assumption, both of these get mapped to 0. So we have 0 plus 0, which is equal to 0. And the same here. We have phi of lambda x. By linearity, it's the same as lambda phi x. By assumption, this is mapped to 0. So we have lambda times the 0 vector equal to the 0 vector. And another important notion on linear maps or matrices is the rank of a linear map. And yeah, this notion is much more helpful in higher dimensional vector spaces because there are more possibilities of what the rank of a matrix could be, but it's also interesting to look at it in 2 dimensions already. So we say the rank of phi is 0 if the kernel of phi is the whole plane. So every element of the plane is mapped to 0 by phi. This is just another way of saying that phi is the 0 map. Or if we take it for a matrix, then it would be the 0 matrix with only 0 entries. We say the rank of phi is equal to 1 if the kernel of phi is a line through the origin. And we say the rank of phi is equal to 2 if the kernel of phi consists only of the vector 0. So it's a set with just one element. And we have another theorem, theorem 12, that I alluded to before. It says that for a linear map phi, which is represented by a matrix A, the following statements are equivalent. First, phi is invertible, and that's to be equivalent to the rank of phi being equal to 2, so this situation here. And those two being equivalent to the fact that the columns of the matrix A, which represents phi, form a basis. So the columns of A are linearly independent. And let's prove this. We start with 1 and want to prove statement 2, so we assume phi is invertible. And we want to show that the kernel of phi consists only of the vector 0. Now, let x be any element in the kernel of phi, then A times x is equal to 0, because A is the matrix that represents phi. So phi of x is the same as A times x. Now, we know that A is invertible because we assume phi to be invertible, which just means the same as its representing matrix being invertible. So we can multiply this equation here by the inverse matrix, and we get x. So A inverse times AX is just x. And on the other side, we get A inverse times 0. But any matrix times the 0 vector again gives the 0 vector, so we have x equal to 0. Now, x was an arbitrary element from the kernel, and we've shown that any element in the kernel must be 0. So it's the only element in the kernel. So we have shown that this is true, so rank phi is equal to 2. Now the equivalence of statement 2 and statement 3 is given by theorem 4. Now recall what was stated in theorem 4. So A is the matrix representing phi, and so the kernel of phi and the kernel of A are the same, and that the kernel of A is equal to 0, which is statement 2, means that a unique linear combination making the columns of A to 0 must be the 0 vector, and by theorem 4 this is equivalent to the columns of A forming a basis, and this gives the equivalence of 2 and 3. And now we only need to prove that 3 implies 1, so if we assume that the columns of A form a basis, then we prove that phi is invertible. And we can again use theorem 4 for that. And we conclude that for every vector y, there's a unique solution x index y to the linear system Ax equal to y. This follows from the assumption 3. Now the inverse map is just given by phi inverse of y defined to be x index y. And this is unique, so this is a well-defined map. And yeah, therefore we have our inverse map, it exists, and we know that phi is invertible. And that concludes the proof, because we've shown that 1 implies 2, 2 and 3 imply each other, and finally 3 implies 1, so any of the 3 statements implies any other one. Now let's see how linear combinations of vectors behave under linear maps. So given any vectors x1 to xk and the linear map phi, and we have a linear combination lambda1 x1 plus lambda k xk, and we apply the map phi to this, then we get the linear combination of the images phi x1 to phi xk just by linearity. So if we plug all this into phi, we can pull apart the sums and take out the scalars. So we end up with lambda 1 times phi x1 plus lambda k times phi xk. So we get the same linear combination with the x1s to xk replaced by phi of x1 to phi of xk. Okay, proposition 13. What happens with linear independence under linear maps? If phi is a linear map, then the following are equivalent. Phi is invertible, is equivalent to saying that for any pair of linearly independent vectors x, y, the images phi x, phi y are also linearly independent. And of course the analogous statement holds for matrices instead of linear maps. For the proof, we first assume that phi is invertible, and we want to show that the second statement holds, so that the images of linear independent vectors are again linear independent. So suppose we have a linear combination lambda phi x plus mu phi y, which is the same as phi lambda x plus mu y, that is equal to 0. Now, by assumption, we assume that 1 holds, phi is invertible, so we get, if we apply the inverse to this expression here, we get lambda x plus mu y equal to phi inverse applied to 0 here. But this, of course, is again 0, because the linear map maps the 0 vector to 0. So now we have a linear combination of x and y that is equal to 0. And if we assume that x and y are linear independent, then we have lambda and mu both equal to 0 from this line here. But that also implies that here there must be 0 here, and that is true for any lambda mu that would give us such an equation here. So this means whenever we have this situation here, lambda phi x plus mu phi y equal to 0, it follows that lambda and mu are both 0. So this is nothing else but phi x and phi y being linear independent. Now for the other direction, we now assume that number 2 is true, so that the linear independence of xy implies the linear independence of phi x, phi y, and we want to show that phi is invertible. Okay, so let x be an element in the kernel of phi, and e1, e2 the canonical basis, then x is some linear combination lambda e1 plus mu e2 for suitable scalars lambda and mu. And by linearity, we have 0 equal to phi x because we chose x to be in the kernel. And this is the same as lambda phi of e1 plus mu phi of e2. Now, phi e1 and phi e2 are linearly independent by assumption. So, because we assume statement 2 to be true. So from this assumption and this equation here, it now follows that lambda and mu are both 0. But if lambda and mu are both 0, then this means that x was the 0 vector to begin with. And so we've shown that any element x contained in the kernel must be 0. So it's the only element in the kernel. And by what we saw in theorem 12, this means phi is invertible. And so we've shown that statement 1 follows from statement 2. And in the next example, we go back to studying our projection matrices. So we already established that they're not invertible. And let's look at the projection matrix for the projection onto the E1 axis. And we can easily see that the kernel of this matrix is the line generated by the vector E2. So the kernel is this line here. And we can clearly see that any two linearly independent vectors xy that get projected to multiples of E1, so that get projected onto the same point here, that the images are no longer linearly independent. Okay, so x and y actually get mapped to the same point, but even if we take any point, let's say a vector out here, it would get projected onto something on this line here and would be linearly dependent with any other point on this line. And in particular, what we see, if p1x is the same as p1y, then the difference of the two vectors is an element of the kernel. So here, y and x get projected to the same point. So the difference is the vector here. And this line is parallel to the kernel. So the difference vector between these two vectors that get mapped to the same point is in fact an element from the kernel, from this line. If we add that here, well, we get all the elements being mapped to the same point here. And as an exercise, you can prove that this is a general property for linear maps. So pause the video for a few minutes and prove that if phi is any linear map and we have phi of x being equal to phi of y, then the difference x minus y is an element of the kernel of phi. So this is not too difficult to show. We assumed phi x equal phi y, and by linearity of phi we have that 0 is phi x minus phi y equal to phi x minus y. So this is true by assumption that this is 0, and by linearity this is the same as phi x minus y, and this means x minus y is mapped to 0, so x minus y is an element of the kernel of phi. And another exercise, maybe a bit more involved, this one. Pause the video again and prove that a linear map phi is already completely determined by its images phi b1 and phi b2 on any basis with elements b1, b2. Okay, what this means is that if we have linear maps phi and psi that agree on the two basis vectors, so phi b1 equal psi b1 and phi b2 equal psi b2, then this means that phi is equal to psi. So if phi and psi agree only on these two basis vectors here, then they will be identical on any other vector of the plane as well. And maybe as a hint, look at the proof of proposition 1 in chapter 2 at timestamp 4 minutes, where we proved the corresponding statement for the canonical basis. So I hope you gave this some thought. The solution is here. So suppose there's a linear map psi which satisfies these two properties, that it has the identical values as phi on the two basis vectors. And then we look at what psi does on an arbitrary vector. So any vector x can be written uniquely as a linear combination of b1 and b2. And now we plug this into psi. So psi of x is psi of lambda b1 plus mu b2. Because psi is linear, we can write this as lambda psi b1 plus mu psi b2. Now we use this property here to replace psi by phi. So this is the same as lambda phi b1 plus mu phi b2. And again, by linearity, that's just the same as phi of x. So for any vector x, psi of x equals phi of x, and that means those two maps are identical. Now we've learned a few properties of inverse linear maps and inverse matrices, but how can we find them? Let's find out. And there's actually a rather simple way to test whether a matrix or the linear map defined by it is invertible, and compute the inverse, and it's both in the same procedure. So given a matrix A, and we suppose that the inverse matrix A inverse exists, then if we say the vectors x1 and x2 are the columns of the inverse matrix, so we write it like this: A inverse equal to x1, x2 as column vectors, then that A to the minus 1 is the inverse of A means A times A inverse is equal to the identity matrix. So if we write this out explicitly, A times A inverse is A times the matrix with columns x1, x2 equal to the identity matrix. So if we multiply the first column x1 of the inverse by A, we get 1, 0. And if we multiply the second column of A inverse by A, we get 0, 1. So the first canonical basis vector and the second canonical basis vector, which are just the columns of the identity matrix. Now, this condition here is equivalent to the simultaneous solvability of the two linear systems that we get by looking at the two columns here separately. So for the first column, we get the system A times x1 equal to 1, 0. And for the second column, we get the system A times x2 equal to 0, 1. So in order to determine the inverse, we need to solve these two systems. But if the inverse does not exist, then these two linear systems cannot both be solvable. Let's look at this in an example. So we're given this matrix here, A with entries 11, minus 2, minus 5, 1. And we want to determine the inverse matrix of it if it exists at all. Now what we do, we write out what we had on the previous slide. We attempt to solve the two linear systems, matrix A times the unknown first column of the inverse equal to 1, 0. And matrix A times the unknown second column of the inverse equal to 0, 1. And if we can solve both of these systems, then x1 and x2 are the columns of A inverse. And in solving these two systems, we apply the same steps in the row reduction algorithm for both of them, because the steps are only determined by the matrix A, which is the same in both cases. So we can just write it like this, A and the two right-hand sides here, and solve them simultaneously. So in our example, it looks like this, our matrix A and the one right-hand side E1 and the other right-hand side E2. And now we go through the steps of the row reduction, and I've written it out here. We eventually arrive at the identity matrix on the left, so it is solvable. And this is what we end up with as the solutions for the two systems, for the two columns of the inverse matrix. So we can read off the columns of A inverse from the reduced form on the right, and we find that A inverse is the matrix 1, 2, these being the coefficients of x1, its first columns, and 5, 11, here being the coefficients of x2, its second column. And by the same method, we can show in the next example that this matrix A, with entries 4, minus 2, minus 2, 1, has no inverse matrix. Again, we use the same procedure. We attempt to simultaneously solve the linear systems A with right-hand side E1 and with right-hand side E2. We apply row reduction, but we end up with a 0 row here, but with non-zero entries on the right-hand sides. So the second row here tells us that these systems cannot both be solved, and actually neither of them can be in this case. So because they cannot both be solved, an inverse matrix for A cannot exist. And this means A is not invertible. Now, a little exercise for you. Pause the video for a few minutes and compute the inverse of this matrix here with entries minus 2, 1, minus 1, 1. And perhaps rewind the video and look again how we did it in the examples before, and then try to do this for this matrix A. Now the solution, as before, we attempt to simultaneously solve the two systems of linear equations with A on the left and right-hand sides E1, E2. Explicitly, this system here, we perform the row reduction steps and end up with the identity matrix here, which means both systems are solvable, and the coefficients on the right-hand side make up the coefficients of the inverse matrix. So A inverse exists and has entries minus 1, 1 from our first equation here, and minus 1, 2, second column, from our second equation here. So this concludes the exercise. And it's not strictly required to verify this, but I would recommend, if you compute an inverse matrix, that you always check that you didn't make a mistake in the row reduction algorithm. So what you do is you multiply A by A inverse, and you have to obtain the identity matrix. And we can do this. Now I've written it out in great detail here. You can check that it works. I'm not going to read it all, but indeed we get the identity matrix here. So we did not make a mistake. And if you would not get the identity matrix here, then you know you must have made a mistake in the computation. So that's why I recommend to check your solution. And with that, we're at the end of my video. Don't forget to like the video and all of my other videos, of course, and subscribe to my channel and turn on notifications for whenever I upload new videos. Thank you for your attention, and until the next time.